All right, good afternoon. So I think we'll start with some statics content for today. This lecture time should be following your session with Jim Connis and following the Martin Luther King holiday. So this should be Wednesday, your third class meeting. And again, I'm out of town in Southeast Asia working on the project I'm involved in over there. So you're getting this piece of content via the video lecture mode. So we're going to go back, as we will in some later days as well, looking at some of your statics content that you hopefully had, either here or if you transferred that course from another school in your statics class. This content comes out of Chapter 5 in the Hibbler textbook, which if you took the class here, the statics class here, you would have used this textbook. So hopefully you can reference both the book and this lecture as you tackle the homework, which I will be assigning over this content. So as you can see on the screen, this is contents about equilibrium of a rigid body and resulting free body diagrams. And of course, the key here is really the free body diagrams, which to me are one of the keys to all of mechanics, whether it's statics, dynamics, or the strength of materials or mechanics of materials. This content actually comes from Chapter 5 and sections 1.2, 5.1 and 5.2 in that Hibbler textbook that I mentioned. And so this would be your January 20th lecture. So, get going here with some of the content. What we hope you get out of today will be this idea of support reactions, and we're going to talk more about this in one of the later lectures, and then drawing a free body diagram. Now these free body diagrams are going to basically be two-dimensional, and so we will move to the three-dimensional free body diagrams in a subsequent lecture, which is what you're going to need to be able to do in some part for the suspension of the car that you're going to be analyzing. So we will have these sorts of activities in these videotaped lectures. So this is the first one you've seen. So we will not be checking homework today. I'm talking about that. We would if we had homework or were in a normal sequence of this class. You will have a little what I call reading quiz that will be drawing the basics out of section 5.1 and 5.2. That will not be scored because we are not in class together. If we were, I would be scoring that. We'll talk about applications of this content, this idea of support reactions, which again should be review for many of you, and free body diagrams, again review, and then a concept quiz to see if you've got the concepts, or we can talk about those. Or I will be talking, you will be listening in this case, and some problem solving, which again in class we would typically do as a group problem solve. And then so-called attention quiz, which basically asks, kind of checks to see if you've captured the important content of this material. So a first reading quiz, and these all tend to be multiple choice questions. And so you will get a question, in this case, the first question, if a support, again this is a support to something you're trying to analyze, prevents translation of a body, then the support exerts what kind of something on the body, a blank on the body. So your choices, A, a couple moment, and remember couple moment is statics language for a moment or a torque. In other cases, same units, foot-pounds. Between a couple moment and a torque. In this case, couple moment is the correct language. Force, a simple force. A support could be both A and B. In other words, translation, think about what translation means. Or D, none of the above. So key word in this question is translation of a body. Or key words, I guess, 3, 4 of them there. So think about if a support is preventing a translation, then what sort of thing does a support exert on the body? Think about that for a second. And really the things you have to distinguish here are between A and B, because C, of course, is just a combination of those two. So the key there, and I pointed this out to you, is translation. So if a support prevents translation, then basically it is exerting a force, B, on the body. Okay? Translation translates into a force on the body. So that's one. Let's see what the second one is. Internal forces are blank, shown on the free body diagram of a whole body. So we're drawing a free body diagram. Is there an internal force? Do we show it? Do we not show it? Do we sometimes show it? And you can see those are your answers. Always, often, rarely, never. What happens to internal forces when we think about a free body diagram? I give you these pauses so you have a chance to think, because if you think and try and make a decision, then the learning actually increases. If you try to essentially pre-test yourself, figure out what you think the right answer is, and when I tell you what the answer is, it will actually increase your learning rather than me just going ahead and telling you. So in this case, internal forces, things that are going on in whatever it is we're drawing the free body diagram of, basically are never shown on the free body diagram. Part of the definition of a free body diagram, as you may recall, is that we only show external forces acting on whatever it is we're drawing the free body diagram of. All right, so now some applications of this idea of supports and free body diagrams. So this truck ramp that you can see in the picture here, again, it's kind of like on a tow truck or a ramp truck, has some cables attached to it, has a weight, in this case 400 pounds, and each ramp is the pin to the body, so it's two split ramps if you want to think about it that way. We can only see one in this picture, and held in position by that cable. So the question is, we want to know what the cable tension is and the support reactions to be able to analyze or design or perhaps analyze a failure of what's going on with this ramp and its supports. So how can we determine that? Now you'll see two pictures to the right, and keep in mind that those pictures are used for different things. These are actually two different kinds of pictures. So one is this ideal of an idealized model. Now, perhaps you remember what the idealized model is, but think about it here. We have the picture, and then that next picture, this one here, this next drawing, is essentially our idealized model. We're looking at the truck ramp, or the ramps here, or one ramp, and we have point A, we have the cable and its support structure here, we have the ramp, we have appropriate dimensions. G here, if you recall, is center of gravity, represents the center of gravity of that ramp. That's where we would apply that weight of 400 pounds. And then attachment point B, where the cable is attached. So that's the idealized model. It basically shows us key dimensions and simplifies the more complex setting of the complete picture over here. Now the next one, of course, is the free body diagram. And of course, the key there is that it has these forces shown on it. So the free body diagram, again, recall, is all external forces acting on the thing we are analyzing, in this case, the truck ramp. So we have the tension in the cable, we have the weight, G, and then we have these things, the forces at A, that pin joint, and those are those support reactions we talked about earlier. I already gave you your answer to this. Obviously, it's that one in the center. So a second application here. Now in this case, we've got a fork truck with some tines, or the fork attachment. It's got two pieces of pipe on it, steel pipe. And so we want to understand how the loading works between the pieces of pipe, each other, and then the fork tines on that fork truck. Now, reactive forces means what's reacting between the pipe and the tines of the fork, or the fork attachment on this front end loader. So that's the question here. And again, this thing on this picture here is our idealized model, because we simplify and we draw essentially what's going on. And then we can draw the free body diagram. Here, the free body diagram, we have a force that's acting here. We have the weight of each pipe. And again, these, in this case for pipe, points in the center basically, or G, the center of gravity for those points, for those pieces of pipe. And then we have the reaction force of each piece of pipe on the fork tines. In this case, because it's a round surface here, flat forks, there's only one point of contact. We idealize that by one point of contact, a concentrated force that we call F and P. So this sort of free body diagram is what we have to be able to use to be able to make an analysis of what's going on here in forces. Now again, this should all be reviewed from when you took your statics. So conditions for rigid body equilibrium, or section 5.1. When we deal with a particle, and remember that's what basically most of the content before chapter 5 in the Hibbler book at least focused on, was analyzing particles. All the forces act on that particle, and so since a particle is essentially a point, we didn't have to worry about where the forces were located at. They were all applied to the force. So they are don't necessarily cause any rotation. Rotation of a point doesn't really make sense, but when we talk about a body, something that's got dimensions to it, different from a point, that means that those forces could cause rotation of some sort, could cause the thing to tumble or do something, move as well as tumble or rotate. So for a rigid body, these things with dimensions, not just a particle, to be in equilibrium, the net force and the net moment have to be equal to 0. So to be in equilibrium, again, this is statics, things aren't moving, so all the forces have to balance to 0, thus no translation, key point, and no rotation, which we translate into formulas by saying that summation of moments have to be 0. So if there was a moment resultant, then this thing would be spinning or turning somehow, rotating. But for an equilibrium condition, the forces have to be equal to 0 and the moments have to sum to 0. Now these are shown as vector equations. And you should know vector from your class, what a vector definition is, as magnitude and direction. Or a scalar equation, we can also write these vector equations as scalar equations, and hopefully you remember how to do that. So, simply put, the process of solving these rigid body equilibrium problems are, we have an idealized model, in this case we're calling up our truck ramp, and then we have to create this free body diagram that shows again all those external forces. And they could be active. Active means they are, somebody's applying a force, something's applying a force, and reactive forces. So I got a question for you. In this free body diagram, which we have again provided to you, same one you saw before, let me ask you, which are the active forces and which are the reactive forces? Again, I hope you're thinking about this and making your picks. Okay, reactive, remember we talked about reactions at supports. So the way I keep track of it is, at least in my mind, is reactive forces happen where the supports are at. Okay? So we have the two reactive forces at the pin. We have a reactive force, if you want to think about it, at the cable. And then we have what I think of as the active force, and that's the weight. If we had something else hanging off of this thing, that would be another active force. So normally I think of active forces as those external forces. The reactive forces are things that are happening because of a support. So then we have to apply the equations of equilibrium and solve for any unknowns. So since we know the weight in this case, we have three unknowns, the tension and then those two reactions at pin A. So, free body diagram. We have a beam stuck in the wall. So point A, it's stuck in this wall. We have a 1,200 Newton force, 2 meters out along the beam, which has a total length of 6 meters. So this would be our idealized model. Now think about what's going on here. So our active force, that 1,200 newtons, from something has been created, that force. Could be a person, could be a heavy person, could be some sort of distributed load that's been reduced to that single concentrated load. We don't know what it is. But at this point, all we know is we've got a 1,200 Newton force out there. And we've got, of course, the weight of the beam at its center of gravity. And then we have whatever's going on at A. Now, hopefully from your review, this again should be a review, so hopefully from your statics class, when you have something stuck in a wall like that, or something that's embedded in something, that means that's a fairly complex reaction. So let's look at our free body diagram. So to do that, we draw this essentially outline shape. This is our beam. Okay? That's the ideal, that's the beam, and we are drawing the free body diagram. So the other key thing is we have coordinate system we have established. You have to show that for when it comes time to solve these. We won't be solving these problems in this section. All you'll be doing is drawing free body diagrams, but always establish that coordinate system because it's a good practice. Moving from left to right, the supported A, because it's stuck in that wall, we have both forces, a reaction in the A and the X direction. And it doesn't matter which way you show those, positive or negative, depending on which way you've set up your coordinate system. The standard right-hand system we've got that's shown here. And again, that right-handed system is pretty typical. And then you've got the moment at A, because when it's stuck in the wall like that, it can resist rotation. So when we're resisting rotation, then it becomes a moment, a support reaction moment. So the moment being exerted by the wall on the beam prevents the beam from rotating. In this case, the beam would rotate like this out of the wall, in a sense because of its weight, and that 1,200 Newton force would push the beam down. So the wall is helping the beam resist that rotation, so there has to be a moment at A. And then the 1,200 Newton force, and here again is the weight. And again, the appropriate units for weight is newtons, in this case, since we're in the metric. So that's the effect of gravity acting on the beam. This is the applied force acting on the beam. So we imagine this body is cut loose from the wall. It's been detached from the wall, but we draw then the reactions that are happening at the wall. And then it's showing all of those forces. So the applied forces, the weight of the body, support reactions. Same drawing, everything the same. So it's important on your free body diagram to label dimensions and the loads. So you label them, in this case, the AY, AX, M of A, the G and the gravity force acting there in terms of the weight, the external load, establish directions, put dimensions on there, 2 meters, 3 meters, so that you know these critical elements to being able to solve the problem. Any unknown, typically you tie back to the point, so it's an unknown force, A sub X, A sub Y, M sub A, and the necessary dimensions. So there is a table, 5.1 in your book, that gives all these support reactions. You may have some of those committed to memory, but others you may not. So use of a table like this would be very appropriate, or whatever textbook. I guarantee if you have a statics textbook, it will have these tables in it. It may not be table, same label, and it's a table 5.1, but it will have such a table. Sometimes they're actually in the cover of the book. Sometimes they're back in the chapters. Hibbler's case, I think they're all in the chapter itself. So a roller. Rollers, by implication, allow things to roll. So there's no resistance force in terms of a direction along this, but there does prevent translation in or out, or at least into that surface. So there has to be a reaction force, as you can see the way they've drawn it here. Smooth pin or hinge, only the two X and Y in this case, since we're dealing with 2D forces. And if we're stuck in that wall, the fixed support, the X, the Y, and then the moment force. So we have these forces there. There are other more complex cases, rollers, that sort of, not rollers, but trying to think. We'll see one in an example problem here in a minute. We'll see if I can come up with the name of that to support at the time. So again, this general idea which I introduced earlier is if the support prevents translation, you get a force. If rotation is prevented, you get a couple moment. Those are two key concepts to keep in mind. Rotation, preventing rotation means you get a moment. Preventing translation means you get a force. So an example. Now, again, this is a picture on the screen. Hopefully you'll be able to see it, but there's basically a foot here. And that foot is putting a force down on this linkage, which stretches a spring, pivots around point A basically. There's a cable attached at B and a spring attached here, as you can see. So this force, the operator puts a vertical force on the pedal, the spring stretches, and the short link in A to B is 20 pounds. So draw the idealized model in the free body diagram of the foot pedal. So the idealized model, again, we have the force here, and we have all of this information. We put in the essentially the K for the spring of 20 pounds per inch, dimensions. And again, this was not given to us up here. We're having it kind of comes out of nowhere in this case, but this is what the idealized model is. This is sort of information you need. A lot of it's geometry based. And then the free body diagram. So again, the force, and then we have the reaction at A, the pin, and AX, AY, and then we have the 20 pounds here, and this 30-pound force that came out of nowhere. So where did we get the 30 pounds force? Actually, that information was given. We have a 1.5-inch deflection, and down here it said 20 pounds per inch. So the 30 pounds actually came from the spring equation, which you may or may not remember, but basically K times X. So the force in the spring is the spring constant times the deflection of the spring, which is the 1.5 times the 20 pounds per inch. And so we end up with the 30 pounds in the spring force. And again, because we are stretching the spring, basically that force in the spring is trying to pull that pin, this link back, so we get the 20 pounds directed to the right. Don't worry about trying to pick the right direction if you didn't learn this in statics. There's only one case where it's essential that you get the right direction, and that's friction. For the most part, we're not going to be worried about friction in our project, so you can guess the best you can in terms of direction, but the mathematics will work it out and show you the right direction. The only time that's not true, as I said, is with the friction force. So another example. So a crane has a platform being suspended off of an oil rig. It's claimed in this case, we can't see that. Platform has a mass of 200 kilograms. So again, draw that idealized model and the free body diagram of the platform. So the idealized model of the platform is considered in two dimensions because all of the loading and the dimensions are symmetrical about a vertical plane passing through it. That's a subtlety, right? Now, it doesn't have to be that way, but it can simplify a problem for us. Don't worry about that in this context. That's part of your challenge, though, is going to be thinking about your suspension when it comes time to analyze that and make some of these sorts of decisions. But keep in mind that then we will have talked about three-dimensional equilibrium, three-dimensional situations, And so you won't need to make a simplification to get it to 2 dimensions, because you'll be capable and want to analyze the suspension in 3D. Although keep in mind that you can take pieces of a 3D item, a 3D machine, say, or suspension, and analyze it as a 2D case, depending on the situation. So always have in mind that it's context driven, whether it's a 3-dimensional or a 2-dimensional case. It depends on the context of the problem. That's why you're an engineer. That's why you're studying this stuff, is so you can help make those conceptual decisions. So the connection at A is treated as a pin. Now, again, in this case, going back, it wasn't evident in the picture, but there's a pin here, and that's the pin that they're talking about at A, and then these cables that go up. So get our picture back. Here's our frame of the actual platform here. It has a center of gravity, G there in the center, our pin joint at A, and of course the cable that's attached at B. So the cable supports it at B, connection at A is a pin, and we've assumed these directions. Of course, G represents the center of gravity, and hopefully in your statics class you had information on how to actually find G for more complex shapes such as this, typically using that table method that hopefully you remember. So we've assumed some forces, so let's look at our free body diagram, and you might even think about, well, how would I draw that as a free body diagram? So pin at A, an A sub X and A sub Y, no moment because it's a pin, it can rotate. That's why we got to have the cable, in fact, is to prevent it from rotating. Cable breaks, the whole thing's going to pitch down, throw the people overboard. And then we've got the weight, which is our, what was that? Think about it. What did we have back here? We had a mass of 200 kilograms, right? Mass is not weight. Hopefully you remember that. So that's why this number representing the force, the weight at G, is 1962. So that is the mass times the gravity. So remember, weight equal mass times gravity. So we had to take the mass of the platform, multiply it times 9.81 meters per second squared, the constant of gravity in metric units, to come up with that 1962 newtons. So again, we've got some key dimensions on our platform. Again, those were not given to you in the picture. They come off the idealized model that we've got here. The tension at the cable at B, this is point B, and then the supports at A. So that's our free body diagram. And we've assumed the cable direction, and we've assumed the directions of A, force A sub X, A sub Y. Now, when you've got a cable, there shouldn't be any difficulty figuring out which direction it is, right? Because you may or may not have heard this old saying, so I'll give it to you now. You can't push a rope. So a rope or a cable is only able to carry a load in tension. So that has to be holding up the platform, the direction, that tension force in that cable has to be acting in this manner off that platform. The cable can't be pushing the platform, in other words. So your concept quiz. So we again have a beam. It is pinned at A. Okay. You can see or may not be able to see, but there's a pin at A. It has a cable that connects here at B, goes up over a pulley, and we assume a frictionless pulley as shown in the problem, at D, and then down to a connection point at E. So the cable is fixed at B and E, and then out here at C we have that external load, 80 kilograms, given to us in the problem. So the question here is, in a free body diagram of only the beam, there are how many unknowns? Things you do not know. Notice it doesn't say total. It's not asking you to draw the free body diagram. It's just asking you what would be on this free body diagram? And so I'm going to give you a hint, work from left to right, as we've been doing, and total up what forces, what sort of reactions, moments would be happening across this beam. So think about it, and then look at your answers and make your pick. Okay, you may not be all the way through, but let's take it again from left to right. What have you got going on at A? Pin joint. So two forces, right? An A sub X and an A sub Y. What do we got going on at B? Well, we got a cable attached there. So there's going to be a force, right? So we got a force. E. What do we got? Again, same cable, so one force. And again, we asked about unknowns. This is a known force, so we don't care about what's going on at C because it's a known, so we're not interested in that. So now, if you said, okay, 2 plus 1, that gives me 4, you would have picked D, and you would have been wrong. Anybody know why? Do you know why? Think about it. Okay, the reason you're wrong is these forces are equal. It's a cable over a frictionless pulley, so that means the force at B is the same as the force at E. So again, we were counting for unknowns, things we do not know. So really, all we have are 3 forces. The 2 at A, and this one force, tension at B has to equal the tension at E because it's that cable going over the frictionless root. So, second question. All right, we got another link. It's got a roller at A, a pin joint at B. In case you can't see that, but that's what you got. You have a moment in the middle of this force, 800 pounds, again, acting in this direction, essentially counterclockwise. You have an external load, 390 pounds with some geometry attached to it. So if the directions of the force and the couple moment, so the force and the couple moment are changed, in other words, reversed. So now the force will be in this direction and the couple moment will be in this direction. What will happen to this link, this beam, piece of metal? Read your answers. Hopefully this one was pretty easy for you. Again, let's think about it. The beam will lift from A. Well, yeah, actually that probably will happen. If I put a moment on that beam, it's pinned down here at B, so it's going to rotate. There's nothing at A to keep it down. A only prevents it from going this direction, right? So it cannot go that direction. So if I reverse it, it's going to lift. So the right answer is A. We made it easy for you. We put the right answer the first there. Cannot lift from B because it's pinned. The beam will be restrained. No, actually it won't be because it can move. The beam will break. Why would it break? Because it can move. If it can move, there's certainly no reason for it to break. All right, so in this case, we have another problem, and again, we have this kind of oddball piece of pipe stuck through a hole. It has a contact point here at C, contact point at B, contact point at A. And those are basically point contacts, the way we are assuming, simplifying this, and you can see the dimensions are given to us, even if you can't read them on the screen, and 300 Newton force over here. So that force, it can't pull through because it's got this hook on the piece of metal or the pipe. So what's going to happen, and what we want to do, have you do, is draw a free body diagram of this smooth pipe. Now that's code for saying that there isn't any friction, which rests against the opening at those 3 points that I already highlighted. So I want you to draw a free body diagram of that. Now think about those external loads. All right, what would be happening at those points of contact? And again, it's a smooth pipe, no friction. And it might even be worth your taking a second with a piece of paper and a pen, just trying to sketch that out, either now or take it up again, or because you'll be doing it in your homework. Okay, here's your idealized model. So your decision is what's happening at C, what's happening at B, what's happening at A. That's what you got to draw in your free body diagram. How are those supports interacting with or preventing something from happening at those points? So here's our answer, the free body diagram. Of course, you got the 300 Newton force that's being externally applied out there at the end. Because these are smooth, no friction, essentially a knife sort of joint, as you may have heard them referred to in your statics class, you got only a normal force at each point. So you've got 3 normal forces at each point. There is nothing else really going on here. So it's a relatively simple free body diagram. So another problem. We have a slider here at A. That's the one I was trying to think of earlier. Basically, it's a frictionless sort of bearing, if you want to think about it. At A, on that smooth rod, we have an external load of 100 pounds, and we have a 200 foot-pound couple moment applied out here, and we have a smooth contact point at B down here on that inclined plane. So I want you to draw a free body diagram of this bent rod, and you can begin the smooth surface at B, collar at A, which is fixed to the rod and free to slide over the fixed inclined rod. So drawing a free body diagram there, you've got essentially some sort of support here at A, a support at B. So those are really the only areas where this thing is supported, and you've got those externally applied couple moment and force to worry about. So your idealized model, which is essentially what we had up on the screen a little earlier, and then your free body diagram. So because that collar can slide at A, there is no force up and down the rod, and so we only have that normal force R sub A. So we know its geometry based on the geometry of the rod. Of course, the external load, a couple moment, and because this again is a smooth surface at B, essentially it's like a roller, so we only have the normal, or the resultant force there, the normal force. Its orientation again is known because we know the orientation of the ramp. So fairly straightforward. Again, no only normal forces. Keep in mind that these supports, you may think, well, why isn't there, either in this one or the previous one, why is there no moment? Okay, why are there no moments acting on this thing? And again, it's because these supports don't necessarily inhibit a rotation. All right? So your attention quiz. Internal forces are not shown on a free body diagram because the internal forces are, and choose the most appropriate answer of, equal to 0, equal and opposite, and they do not affect the calculations, negligibly small, or just not important. And hopefully, we've talked about this several times, you recognize the answer is B. They are equal and opposite, they are internal, that's why they're called that. And a free body diagram only shows external forces. Two, how many unknown support reactions are there in this problem? Now the problem here is we have a bent piece of metal stuck in a wall at A. Has a Distributed force, as you can see, over that 3-foot length. Then it has a 30-degree angle up here. And it has a roller at B. So stuck in the wall at A, roller at B. Those are the supports. So the question is, how many unknown support reactions are there? And so I would suggest you tackle this one just as we did earlier. Start from left to right and see what you come up with. Hopefully you got this one because we've done several similar ones. So what do we have at A? We have essentially two forces and one couple moment, right? Because it's stuck in the wall. Resist couple moment and two forces. What do we got at B? It's a roller, and so that can only essentially support a normal force. And so we have 2 plus 1 force, 3 forces, 1 couple moment. So your answer is D. So hopefully this quick review of free body diagrams and the support reactions kind of brings statics back to you a little bit. Your next lecture, statics content, we will take this a step further, move into a little more complex situations. Again, we're plucking pieces of statics that will either be a review, depending on the class you had, or, again, depending on the class, maybe new content. Hopefully you did keep your statics book and you have that on your shelf to go back and do a little extra study if you need to. We will be posting homework problems, in this case from the Hibbler book, up on the Blackboard site for the class for you to tackle. In this case, the homework problems will be essentially drawing free body diagrams, just like we've been practicing here in this video lecture. And so you may find a book as useful, or you may be able to do it without a book, depending on your knowledge and how much you remember. But these are skills that you will need to be able to accomplish that suspension analysis that Mr. Conness talked to you about on Wednesday, and so last Wednesday. So hopefully you've had a good week, and we'll have a good rest of the week. And I will hope to see you eventually. Should in fact be next week. I should be able to be back and be able to see you next week.